Log on, tune in, find out. Another good idea from Cambridge.
Every node in those networks has ancestral or current species, whereas other kinds of phylogenetic networks have been defined, abstract ones, and I will try to show some links between the two. So I think yeah. So I will first present those two types of networks in more details, then focus on level K networks, and then show some results on how circular split systems are linked with unrooted level 1 networks, and finally speak about reconstruction of those networks from triplets and quartets. So this is what I was telling you about those abstract networks when it loads. Well, sorry, it's okay. Yeah. So here you have those networks where it just displays data. You cannot interpret those inner nodes as ancestral species, whereas here in those networks you can. Those leaves are the current species, and the other ones are the ancestral ones. And those methods to reconstruct those networks were developed quite independently in the last 30 years. And I will now focus more on the split networks, where the way to read them is that each set of parallel edges represents splits between the taxa, so a bipartition. So here is one example. Here is an example of incompatible splits, and also the cut edges of this graph represent splits between the taxa. So in fact, you have many different restrictions on set of splits, and you can represent those set of splits by the split networks I showed you earlier. And you also have different restrictions on explicit rooted networks, which were introduced both to model biological constraints and also to get fast algorithms to reconstruct them. And I will focus more on those two classes of restricted networks. So what are those level K networks? In fact, you can define the level in the following way. You have those blobs in the networks, which are in fact the reticulated parts, more precisely the bridgeless components of the underlying graph of this rooted network, the underlying undirected graph. And you count the number of reticulations inside those blobs, and the maximal number of reticulations among all the blobs is the level. So this is a level 2 network, and a level 1 network was introduced under the name gold tree by Gusfield, and it's simply a tree of cycles, a rooted tree of cycles in this case. And so this level expresses how far the network is from a tree structure, and this will lead to fast algorithms. So we tried to extend this definition to the unrooted networks, explicit still, where you can still interpret the nodes as species. And the idea here is to go to the edges and to say that it's the maximum number of edges to remove per blob to obtain a tree. So here, for example, in this blob you have 2 edges to remove to obtain a tree. So and it's a maximum, so it's an unrooted level 2 network. And in fact, this parameter, the number of edges to remove, is the cyclomatic number of a graph. So the level is just the maximum cyclomatic number of the blobs. And level 1 networks, unrooted, are just tree of cycles, unrooted. And in fact, you can see those networks as really trees of blobs, which can be summed up by very simple graphs that you take from a dictionary of level K generators. So when you fix the level, you build those level K networks as a tree of those generators. And if the network has level 2, then you only have one generator. So you just put them together with also tree parts and also simple cycles. And when you go to level 3, then you have 2 other generators to obtain more complex structures. So using this decomposition, this tree structure, can lead to enumeration results and sample and still obtain the number of unrooted level 1 networks, an explicit formula given the number of leaves, cycles, and edges. And so first with Mathilde Bouvel, we extended this to obtain an asymptotic evaluation for those labeled level 1 networks and unrooted. And then we counted the number of rooted level 1 networks and with also an explicit formula. And then we generalized this enumeration framework to get the number of unrooted level 2 networks. And as well, an explicit formula, but quite complicated with the 6 sums here. And still it gives the number of the first, so the number of networks on n leaves when they have level 1, rooted or unrooted, or level 2. And so you see it's much bigger than the tree space here. I didn't mention that, in fact, the level in the unrooted and rooted context are exactly the same. The thing is not completely trivial, because to go from unrooted to rooted, you have to choose a root, of course, but then you also have to choose an orientation of the edges inside the blobs. And in fact, you have many ways to do this. So one unrooted network could, with the same routing, the same edges chosen to root it, could give two different, well, at least two, in fact, an exponential number of level k rooted networks. So in each case, in fact, the level, the rooted level stays the same, so it's an invariant, it's really the same parameter for the unrooted and the rooted context. Now let's go to the links with split systems. We have to define the splits in those networks, because the split networks I presented earlier were different kinds of networks where you had those parallel edges. Here you want to have this unrooted level k networks and find the splits inside, and two definitions appeared in the literature. One would be to take the split of a tree contained in the network by Woolley and his co-authors, and the other idea would be to take the minimal cuts of the network. And in fact, we proved that the two definitions are equivalent, because you see that this bipartition GF against the other leaves can be represented as well by a simple minimal cut in the network. So now that we have defined splits in those unrooted explicit network, why is it better or interesting to have this new definition? Why not just use those split networks? Well, if you consider that this is the real network which represents evolution between those 9 species, usually what people do is they extract the gene trees. So for example, we have those two, and before, when there were just split networks, people would put those trees into split tree and do a consensus network, and you would obtain this split network. So then biologists would find it quite difficult to interpret, because here you see a very complex situation, whereas there is only one reticulation. And here, if you say, let's find an unrooted network which contains all the splits, then you obtain a very much simpler one, which reflects reality a bit better when you want to visualize them, those splits. Now let's go to the link with circular split systems. So if you have an unrooted level 1 network like here, I haven't defined what a circular split system is. The thing is, there must exist an ordering of the leaves, a circular ordering of the leaves, such as the one shown here, where each split appears as a bipartition between two circular intervals along this order. So here, for example, you have this split GF with another interval of leaves on the other side. And in fact, the interesting thing is that the splits of an unrooted level 1 network are circular, and also that if you have a circular split system, then there exists a level 1, an unrooted level 1 network, in fact even one with only one blob, one cycle and hanging leaves, such that this split system is contained into the split system of this unrooted network. So now let's go to the reconstruction from triplets and quartets. the usual framework nowadays can be this one, which is we start from the gene sequences and in fact identify the families of homologous genes. For example, here the families G1 and G2. And then for each gene family, we reconstruct a tree. And this was popularized because now we have huge masses of sequences, and we can, instead of storing them and dealing with them with our algorithms and programs, store more a database of trees, like the whole genome database, which was used in our project Philarian. So you have those databases of trees, and you try to put them together inside a network. So this network should contain the trees and should be optimal in some sense. So either minimize the network, the level, or minimize the number of reticulations, the nodes with two parents. The problem is if you want to minimize, for example, the number of reticulations, it's already an NP-complete for two rooted trees, whereas here we are facing databases with lots of trees and lots of species. So an idea was to not go directly from the trees to the network, but to explode the trees into the triplets and quartets they contain. So here is the definition of triplets A separated from C, just a rooted tree on 3 leaves contained into the network, or into the tree. And the quartets is just the same, so it's just unrooted and it's on 4 leaves. And so here is the quartet AB separated from CE. Now, if you want to reconstruct by going through this indirect step, will you obtain the same network as going directly from the tree? Well, in fact, we have the same phenomenon with quartets than with triplets. It's not the case because this network does not contain the tree on the left, but it contains all the quartets of the tree. So in fact, you won't get exactly the same network, but if you consider all the networks which contain the trees or the triplets or the quartets, then the set of networks here obtained directly is included into the set of networks which contain the triplets and quartets. So when you take the optimal one, this one will be simpler, so we'll have less reticulation or a lower level than this one. So it's a kind of optimistic situation that you are reconstructing by going through this indirect steps. So many algorithms were developed on triplets already. So only finding the triplets, there is an optimal algorithm in cubic time. And how do we do for quartets? Well, in fact, the key here is to notice that having a quartet AB separated from CD in the network is the same as finding 2 disjoint paths in the network, one path from AB and one from CD, and then we can just use the algorithm, the best one known actually currently, for the graphs of degree less than 3 by Soleil, and this is in almost linear time. Alpha is the inverse of the Ackermann function, but let's say you do this, so for all quartets you get the whole quartet set in almost O of n5, but let's say O of n6, and Soleil is quite confident that he can get the whole quartet set in fact O of n4 by some clever preprocessing. So now let's go to the reconstruction of trees or networks from quartets and triplets. You see that there is an interesting dichotomy here, because in the general case it's NP-complete from quartets to reconstruct an unrooted tree, whereas it's polynomial for triplets. And in fact, when you go to a dense data set, which means that you have for every subset of 4 leaves or 3 leaves, there exists a triplet or a quartet in your data set, in your input, then it becomes easy. And for example, you can use this algorithm by Berry and Gasquel to reconstruct the unrooted tree, or an optimal one also, or at least, yeah, an optimal one because you have all the triplets by Aho and its co-authors. Now, if we go to networks, you can see that, so still we have the level here, level 1 and level greater than 1, and you see that lots of different authors, well, papers were published on those networks, because each time you had a new challenge to solve. And the thing is that here we managed to adapt some of those results, some of the ideas used here, but some others can't, well, currently we didn't find how they could adapt to the unrooted context. So what we can do is notice that it is NP-complete to reconstruct an unrooted level 1 network from quartets, but when we have density, it's possible to find the decomposition of the network into blobs thanks to the quartets themselves, and when it's complete, then we can reconstruct it completely, this level 1 unrooted network, and decompose the network when the level is greater. So the idea is to use the equivalent of SN sets, which were introduced in the rooted context. The thing is that this gives you a decomposition of the quartet set when it's dense, and this decomposition is into a tree, an unrooted tree. And it can be obtained in O of N4. And so this is the tree that you obtained from the quartets, and we showed that in fact there is a bijection between the edges of this tree and the cut edges of the network that contains all the quartets. So we managed to find the decomposition of the network knowing the quartets, the whole quartet set. Now the problem is, how do you reconstruct, once you have decomposed it, the inside of the blobs? And here we can use kind of quartet puzzling, circular puzzling. The idea is to put the four first leaves. It doesn't matter which ones you choose, but if it fits into a level 1 network, then you will find the configuration along the cycle, and then you add the edges, the leaves, and each leaf you add, you test all possible positions on this cycle, and this is the kind of quartets you expect, and if you find them, then it's okay, you put it here. I will finish with the dense case, when we don't have the whole quartet set but just a dense set. Then it's linked with the betweenness problem, because the betweenness, we heard about it yesterday, you have a set of elements and constraints on these elements, and you want to find an ordering which respects the constraints A is between B and C. In fact, the non-betweenness problem is the equivalent when you have non-betweenness constraints. And here the quartet problem fits a quartet set into a level 1 network is like the circular non-betweenness, because here you notice that you don't want to have A between C and B seen from D, and this corresponds to, here are the only possible case that you want, and in fact those cases are exactly the presence of the quartets AD separated from BC. So what we need to do here is just find what is this circular non-betweenness in the dense case, and this is an open question. It's interesting to see that this one is also an open question, non-betweenness in the dense case, and I'll end my presentation by showing you my co-authors for those results, and an extension of the tree cloud. So you take the article where those results were presented, and you just show the words on a reticulogram.
Time for one question.
If density is maybe not enough to construct unrooted networks from quartets, what might be a restriction which makes it tractable?
Maybe more restrict on, well, I don't know if we can find any mathematical restriction directly. Maybe it will just be heuristically that you will have enough quartets. In some cases you will know that there are 2 quartets, and as soon as you have 2, it's enough to set up the whole ordering of those 4 leaves along the cycle. So maybe if in some subsets you have 2 quartets, then it's enough. Maybe we have some probabilistic way of expressing this, but I don't think an exact way.
Okay, well, thank you very much.